In these class notes, we're going to take some more looks at rational functions, and we'll also introduce kind of a new idea involved with these rational functions as well. But we'll start off with something that's really not different than the examples we looked at in the video notes, but this is a good opportunity for you to kind of test yourself to see if you're really feeling good about all the different concepts that were presented to you in that last video. So I encourage you to give this one a shot. Try to get an accurate graph down below. All right, so remember we're looking for a number of things here, right? We know that we need to figure out zeros and vertical asymptotes for sure. So whenever we want to do that, if we can factor out the top and bottom, that's always really helpful. And on top here, I can see that a 2 can come out of each of the terms. So that's probably a good place to start. And then on bottom, I can pull an x out of each term. And then I can factor this further. So this is going to be x plus 2, x minus 1, and x minus 1. Now, let's remember what it means when we have the same factor on top and bottom. If this was just an algebra problem that we were trying to simplify, we would just cross these two out immediately, right? But what we note is when we're looking at a rational function, what this means is that, yes, they cancel out. And so they don't have a lot of effect, or really any effect, on the graph except for at one place, and that one place is at x equals 1, right? So yeah, they don't really affect the graph. Really, the graph does just look like 2 times x plus 2 over x, with the exception of the fact that 1 is not in the domain of this function. So what we would say here is that there is a hole at x equals 1. Okay, so bear that in mind as we go to sketch the graph of this. Then, of course, this x here, right, is a vertical asymptote. X equals 0 is a vertical asymptote. And then this is telling me my 0, right? Whenever we make the top 0, which we do by letting x be -2, that gives us a 0. All right, and then the only thing that we haven't really addressed yet is the horizontal asymptote. So remember, our rule is if these highest degree terms have the same power on top and bottom, then our horizontal asymptote is found by taking the coefficient in front of the top highest degree term divided by the coefficient in front of the bottom highest degree term. So y equals 2 is our horizontal asymptote. All right, so with all that information, we're able to get a sketch of this graph now. All right, so let's put in some tick marks here. So remember that your tick marks don't necessarily have to be equidistant apart in terms of the x and y values, right? It's okay if you want to make the y tick marks closer together than the x, that's totally fine. Just know that there will be a little bit different look than you would see if you looked in the calculator. All right, so we've got that horizontal asymptote at y equals 2. And so remember, that means that on the edges, as x goes really negative or x gets really positive, we're going to end up with the graph approaching that line. And then we have a vertical asymptote at x equals 0. And this is the one time we don't write it, is if it's sitting there on the x equals 0 or the y-axis. Okay, we do have a 0 at -2. All right, and then the only other thing that we want to consider here is we know we have a hole at x equals 1, but we want to be really accurate with where that hole actually goes in terms of its y value. So remember that generally this graph behaves like 2 times x plus 2 over x. So in order to kind of figure out what the y value of where the hole should be is at, we're going to plug in x equals 1 just to this part, right? So the part essentially after canceling out those x minus 1s. And so you see we get 6 when we do that. So what that tells me is I'm going to put a hole at x equals 1, but it's actually going to be at y equals 6. So 1, 2, 3, 4, 5, 6. So there's our hole. And the nice thing is that actually gives us something concrete to latch onto, because now I know over here, right, that I need to approach this vertical asymptote and either explode up to infinity or go down to negative infinity. Well, now I know I'm exploding up to infinity. And then this one is not going to cross the x-axis, otherwise I would have found a 0 here, so it's just going to basically follow my horizontal asymptote. And then over here, because I know I have to follow my horizontal asymptote, ultimately I know that it's got to be positive up here. And since it's going to cross at the 0, it's going to be negative there, and so it's going to look something like that. Right? And of course, there's nothing wrong with plugging this into your calculator and just verifying that this is the correct type of look. I have no problem with that at all. Just do remember when you're doing these problems, and let's say you're doing an assessment, then I would want to see all of this as evidence that you understand where all these pieces come from, right? So I should see you acknowledging where your zeros are coming from algebraically, where the hole is coming from, where the vertical asymptote and the horizontal asymptotes are coming from. All right, so let's take a look at this one here. And right away, I want you to notice a difference between this problem and the ones you've done so far. We've talked a lot about horizontal asymptotes, and remember the rule we gave is that if the degree of the top polynomial is smaller than the degree of the bottom, then your horizontal asymptote is at 0. If the degree of the top and bottom are the same, then you take the ratio of the coefficients in front of the leading terms, right? That's what we did here, right? 2 over 1 was the horizontal asymptote. Okay, but what happens when we end up with the degree on top being higher than the degree on the bottom? The answer is we go back to a concept we've already learned, which is long division. And the reason that we're going to do long division is because it'll be a way for us to re-express the way this function looks. Okay, and maybe that'll help us to kind of understand how this thing is going to look in a different way. So remember with polynomial long division, right? If one of the terms is missing, I want to go ahead and write it in there as a placeholder, so 0x. And then we're saying what times x squared gives me negative x cubed, and the answer to that is x, right? Or negative x, excuse me. So negative x times x squared is negative x cubed. Negative x times negative 2x is plus 2x squared. Then we subtract, and so we end up with 4x squared as a remainder. And then we just go ahead and drop these down, plus 0x minus 5. Play the same game again. Okay, I would need to multiply by positive 4. All right, so we end up with 8x minus 5. Okay, so what does all this mean again? It means that this function up here is also equal to, let me write it actually down here, r of x also could be written as negative x plus 4 plus 8x minus 5 over x squared minus 2x, right? So this is the remainder out of x squared minus 2x, right? Think of like when you're writing an improper fraction as a mixed number, right? You're taking the remainder over your denominator, or what you're dividing by. So this is the new function. Now, let's remember that as x goes to plus or minus infinity, then the bottom here is going to get to infinity or negative infinity a lot faster, right, than the top because of the square down here, right? So when the degree on bottom is small or bigger than the degree on top, then everything goes to 0. So this goes to 0 when that happens. Then what we say is r of x looks like this part right here that's just left over. It looks like y equals negative x plus 4. Okay, so what is happening here is that this answer, this quotient that we got, is taking the place of our horizontal asymptote. Because it has a variable in it, though, it's not horizontal. It's what we'd call a slant asymptote, or sometimes you hear it referred to as an oblique asymptote. All right, so here's what's going on. I'm going to go ahead and graph this before doing any of the rest of the function, and I'm going to go ahead and put some tick marks in here. So we'll go ahead and let's do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6. Now we can graph this, right? Y equals negative x plus 4 means that I have a y-intercept of 4 and a slope of negative 1. So down 1 over 1, down 1 over 1. Right? We quickly get a nice picture of what this thing looks like. So this is an asymptote now, just like our horizontal asymptotes before, right? It's just that when the degree of the top is larger, we need to do polynomial long division. Now, before we graph anything else, okay, let's go ahead and put this in our calculator, so we can make some sense out of what it means to have a slant asymptote. So pulling up my calculator here, we'll go ahead and type in, we've got negative x cubed minus 6x squared minus 5 on top, and we're dividing that by x squared minus 2x. All right. Now, as I hit graph here, you can see all sorts of stuff occurring. Let's see here. Oh, I think I typed something in wrong. Let's see. That doesn't look like I expected it to look. So we have negative x. Oh, plus 6x squared. That's why. All right, now let's try it. Ah, that looks better. Okay, so all sorts of stuff going on, and we're going to figure out how we know that all this looks the way it does in a moment. But first, let's zoom out a little bit. So if I zoom out, it looks like that. If I zoom out again, it looks like that. Let me zoom out one more time. Look at that. On that third zoom out, I can't even tell that anything different is going on here besides the fact that I just have this negatively sloped line. So what you're looking at right now is essentially the line y equals negative x plus 4, right? So what we're saying is, in the long run, this graph basically just looks like y equals negative x plus 4, okay? And so that's why that's our slant asymptote. All right, but let's go back and fill in all the rest of the details here. So going back up, okay. First off, let's take a look at the bottom. Let's look at vertical asymptotes. So vertical asymptotes are when we set the denominator equal to 0, right? So go ahead and factor there. So we get x equals 0 and x equals 2 are vertical asymptotes, okay? All right, so we can go ahead and fill that in. I guess I'm not going to put one, or I'm not going to draw it in at 0, but I can definitely draw it in here at 2. All right. Now let's take a look at zeros. Okay, now this is a little bit tricky. What this is actually going to require of us is to remember some of our skills from working with polynomials. So we want to set negative x cubed plus 6x squared minus 5 equal to 0. All right. And so remember, the way we start a problem like this is we go to our calculator and see if we can find a nice one. So let's type in the top of our function. So negative x cubed plus 6x squared minus 5. Go ahead and graph that. Oh, that's right, we had it zoomed out from before, so I'll go back to zoom standard. Okay, and I'm thinking my best bet is this one right here. It looks like that's really close. That's pretty much going right through x equals 1. Let's just verify that by finding that 0. So we get to the left, get to the right. So this is just like one of those polynomial problems where I'm trying to find zeros. So I see x equals 1 as a 0, right? So that's one of them. So that's good. X equals 1. And then, of course, what do we do from there? We do synthetic division, right? So we'd have negative 1 as the coefficient for x cubed, 6, and then we put a placeholder because there's no x term, and then negative 5. All right, so we've got negative 1, 5. Okay, so what we're left with here is we've got x minus 1 times negative x squared plus 5x plus 5, right, is equal to 0. All right, but now that we've got a quadratic, we can, just use the quadratic formula at this point. Okay, so, on the graph here, I'll go ahead and put in x equals 1, right? So we got a point right there. All right, but let's find these other two. So x equals negative 5 plus or minus the square root 5 squared minus 4 times negative 1 times 5, all divided by 2 times negative 1. So negative 5 plus or minus, and what do we get there? When we simplify all that, we get 45 in here, all over negative 2. Now, I kind of like to break these up, like I've said before, so I'm going to put negative 5 over negative 2, so that's positive 5 over 2, plus the square root of 45 over 2, or 5 over 2 minus the square root of 45 over 2. All right, so, and then if I put x equals 1 here, those are my 3 zeros. Okay, now of course I need to know about where these things should go on the graph, so let's just understand that we punch both of these into the calculator and get an approximation. So on this one I get 5.85, and on the other one I get negative 0.85. So going back over here, negative 0.85 is just inside of negative 1. 5.85, 1, 2, 3, 4, 5.85, so it puts me right about there. Okay, and so now I go ahead and I try to work this out. I know that as I go toward negative infinity, I've got to approach the slant asymptote. So that means I know that I've got to do something like this. And then as I get close to x equals 0, I've got to approach the vertical asymptote. So this has to then go through here on this side of the 0. Over here, again, as x gets really big, I've got to approach this asymptote, so that means this one's got to be down here in the negative. And then this one has to approach that vertical asymptote, so it's got to look like that. Now, lastly here, you don't really have anything concrete at this point to be able to determine whether it's positive on this side or positive on that side. So this is where you just got to plug in something, like plug in x equals a half or something like that. And if you plug in x equals a half, you're going to get a positive number. And then if you plug in like 1.5, which would be right here, you're going to get a negative number, so then you're going to get something like this. So this is what this thing looks like on this smaller scale, but remember, if we zoom out, it looks just like this line, y equals negative x plus 4. All right, so let's work one more example here. Here's another one where you'll notice that we've got the degree of the top being greater than the degree of the bottom. So let's just make a note here. We're going to have a slant asymptote instead of a horizontal asymptote. All right, so we know we're supposed to take the top divided by the bottom. So what we're going to actually need here is a whole lot of placeholders, right? There is no x squared term, so 0x squared, right? There is no x term, and there is no constant term. And then we divide by 3x squared minus 27. All right, so 3x squared times, well, it would be 1/3 x would give me x cubed, right? And then 1/3 x times negative 27 would give me minus 9x, which I put under its like term here. So when I subtract, I get a remainder of 9x. Okay, and I can't multiply this by anything to get 9x, so we're actually done. So what we're saying is r of x is equal to 1/3 x plus 9x over 3x squared minus 27, okay? But what does that give me? This part of it, right, this non-rational function part of it, that is my slant asymptote. Oops. Okay. So let's go ahead and fill that in first here. Actually, we should wait. Let's wait on that until we kind of know where everything else is. Where are our zeros? Where are our vertical asymptotes? So then we kind of know how far apart to put our tick marks. All right, let's start with zeros because that looks easy. It's only 0 when the top equals 0, right? So that only happens when x equals 0. And then vertical asymptotes, right? That's when the bottom equals 0. So 3x squared equals 27. And then when I divide by 3, that gives me 9. So x equals plus or minus 3. Okay, and you notice here there's definitely nowhere where we can cancel the top and bottom, so there's no holes or anything like that. So now I kind of know whereabouts to put things. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So right here at x equals 3 is a vertical asymptote. Right here at x equals negative 3 is a vertical asymptote. And then we need this line, y equals 1/3 x. So that means no y-intercept, right? But when I go over 3, I go up only 1. I'm gonna make these ones be a little bit different in their spacing than what I have on the x. So I'm going to go over 3, up 1, down 1, left 3, right? And that's going to give me my slant asymptote. That's where the function's going on the edges. All right. Now, here's the thing. When I'm deciding on this left side, okay, is the graph up here or down here, I actually know it's down here. Why? Because if it was up here, I know ultimately I'm going to have to get myself down to the slant asymptote. So what would I have to do? I would have to cross the x-axis, which would mean there would be some sort of 0 over here. But I already know there's no zeros over there because my only 0 is right here in the middle. So I know this one's got to do something like this. All right. Here I don't really know, right, whether it's positive on this side or negative on this side. So again, we just plug in some numbers. If you plug in a negative number over here, you're going to end up with positive values. And when you plug in one of these positives, positive 1, positive 2, you're going to end up with negative values in the function. And then again, up here, we know it can't do this because then there would be another 0. So then that must mean it does something like this. All right. And let's go ahead and just take a peek at this before we end this example. So what we're doing is saying x cubed, and we're dividing that by 3x squared minus 27. Oops. X cubed, then divided by 3x squared minus 27. All right, and then we graph that. Okay, looks pretty good. If anything, I should have had see how this hugs the x-axis a little bit more than mine does, right? So if I wanted to kind of fix that accuracy, you know, what I should do, this is always a good thing to do, is just to make sure that I'm a little more accurate. Wouldn't take points away from you on a test or anything like that, but I can see that it definitely hugs for a lot longer than I kind of showed it, right? So that makes it look a little bit more like what I'm seeing. All right, but then again, what's the takeaway of this whole slant asymptote idea? Let's zoom out a couple of times. Right, and if I zoom out a few times, then I won't even be able to see all that detail work in the middle anymore. It just looks like the line y equals 1/3 x.